Imagine running a high-traffic database, and a single misplaced keystroke drops a critical production table. In a fraction of a second, vital data disappears. This is the specific failure pgBackRest is built to resolve. It acts as an uncompromising safety net, designed to catch the system the moment user error occurs. This transaction timeline illustrates the mechanism of point-in-time recovery, or PITR. It allows us to rewind the database's state, skipping over the failure to land on the exact millisecond before the table was dropped. To execute this maneuver, you need a running Postgres 15 instance, an active pgBackRest stanza, and a completed repository backup. Real database resilience requires mastering the precise workflow needed to manipulate time and state the moment a recovery is actually triggered. Step 1 is confirming our safety net is actually deployed. We use the pBackRest info command to verify that our full and incremental backups are available on the local cluster. Next, we simulate a healthy operational environment by creating a test table and inserting several rows of baseline data. Now we perform a critical action. We force a manual checkpoint and explicitly record the system timestamp. This provides the exact chronological target we need while the data is still intact. Then the disaster occurs. We execute a drop table command, instantly wiping out the data we just created. Capturing that system timestamp immediately prior to the failure is the foundational piece of telemetry required to execute a successful targeted recovery. Before we can begin to recover, we must halt the Postgres cluster service. Attempting file-level restoration on a running database will cause severe file conflict. We execute sudo system control stop PostgreSQL 15 to bring all background processes to a complete halt. Now we navigate directly into the core Postgres data directory to prepare the environment for the incoming backup. Once inside, we issue a command to completely wipe out all existing contents. Every file and folder currently inside the PG data directory must be deleted. If any files from the compromised state remain, they will mix with the restored files. That cross-contamination causes unresolvable corruption during the restore phase. Completely clearing the compromised current state is the mandatory prerequisite to rebuilding a pristine historical state from the ground up. With the data directory empty, we initiate the recovery using the primary pgBackRest restore command framework. By appending -type = time, we instruct the system to abandon a full recovery in favor of a targeted chronological stop. Applying the -target parameter and pasting our recorded timestamp locks in the precise destination. As restore begins, pgBackRest's delta restore evaluates required files to reach our target, minimizing overhead. Parallel processing accelerates this transfer, concurrently validating page checksums on the fly. The restore command orchestrates a high-speed, mathematically validated reconstruction of the database's exact prior topology. The historical files are now in place, so we execute systemctl start PostgreSQL 15 to boot up the database service. We must immediately tail the PostgreSQL server logs to monitor the specific progression of the startup sequence. We scan the output for a specific log message. Database is ready to accept read-only connections. Following a time-targeted recovery, PostgreSQL pauses in a protective read-only mode. This provides a safe window to verify the data before allowing any new modifications to be written. Once the state of the data is confirmed, we execute the SQL function pgWAL replay resume. This signals the internal database engine to close the recovery process and begin accepting new write transactions. We verify this promotion by checking the logs for the final entry. Database is ready to accept connections. A database is only fully recovered once it has transitioned out of observation mode and is capable of executing new user transactions. We perform a final select query against the originally dropped table. The rows we lost earlier have successfully returned. Because pgBackRest validated page checksums during the transfer, we can confirm this restored data is mathematically identical to the original. Executing this workflow ensures that when a failure occurs, you have a proven, repeatable path to restore services and maintain uptime. Understanding point-in-time recovery transforms a major data loss event into a procedural, manageable operational task.